Hello fellow Scratchers, I'm Griffpatch and today's tutorial is all about demystifying grids and lists. Grid lists. List grids. Storing information in a list, but in the shape of a grid. Seriously though, this gets me really excited and it's just so super useful for creating all sorts of projects. Be that a board game, art project, spreadsheets, mazes with pathfinding or scientific simulations, the list goes on. Grid lists are used in many of my projects. In fact, let me show you. Apple obviously uses a tile grid. It's right there in the very layout of the level. Do check out my tile scrolling tutorial series for more on this type of game. Well, how about this? My sand and water simulator. I love this one. It works on a grid with tiny grid cells where every cell is a particle of sand, water, stone or air. The list behind this project has to be pretty big, don't you think? And you can do all sorts of fun simulations with grids. Have you heard of John Conway's Game of Life? Next up, my port of Slither.io. Wait, this uses a grid? How so? Now this is really interesting. The problem with Slither.io is the number of collectible orbs that appear in the world all at once. Thousands and thousands of them. So many, in fact, that it would cause Scratch to slow right down if we had to consider them all at once when drawing and calculating orb collisions. Instead, the entire level is split up into a virtual grid, stored in a list, and the orbs are allocated to each grid cell using clever bucketing linked list data structures. Whoa. Only the orbs in the nearby grid cells need to be checked, which is far faster. The takeaway? Grid lists are invaluable, even when you might not expect it. Now look back at this pathfinding project we recently covered. We were using clones to create a directional path through a level which sprites could then follow to get from any point to a goal. In this case, it was the apple. But using clones had its limitations. Specifically, the 300 clone limit. Making the path tiles any smaller would exceed this limit and break the project. No, we need another way of storing this grid of directions. This is where lists can come in super handy. Lists don't have to be visible on the screen, and they allow us to store large amounts of information. The only flaw is that we are after a grid of data, something like this, but a list is just a single column of data, like this. Well, this is actually not a problem at all. You see, the view of the list you are used to seeing in Scratch is just one visual representation of the list that Scratch happens to use. For example, we might just flip the list on its side like this. And that doesn't change the fact that item 1 is still A and item 2 is B. So, no, it doesn't matter how we draw this list really. So why not imagine that we split the list up every 3 items and then stack them on top of each other. And voila, we have the same list but reimagined as a grid. This strategy works for a grid of any size. All we need to know to visualize it correctly is how many columns wide the grid is supposed to be. So, if instead of storing letters in this list we store directions, we will have no problem using lists as a basis for our pathfinding projects going forward. Goodbye clones, hello lists. I'm dead excited to show you how to do it. With that in mind, today's tutorial will be an introduction to using lists as grids. We'll learn how to take a hand-drawn maze costume, scan it, and store the walls in a grid list. So here is the actual grid list implemented in Scratch. Each grid cell is represented by a large square tile, 120 by 120 pixels. Now, there's quite a few variables visible on the stage. Don't let that put you off. As you can see here, tile width is, as I said, 120. Next up we have grid columns and grid rows variables. These are letting us know how many tiles wide and tall the grid is supposed to be. This one is 4 columns wide and 3 rows tall, even if the 4th column is rather hidden behind the large Scratch list reporter. Okay then, there's the grid X and grid Y variables. You will notice, unlike the previous variables that we mentioned, these ones change as I move my mouse. That's because they are reporting the position of my mouse within the grid. Not in pixels, like mouse X and mouse Y would, but in grid tiles. You can see how the bottom left tile has a grid X and Y of 0, 0. As I move to the right, the grid X increases from 0 to 1 to 2 and then to 3. Grid Y changes as I move up, also starting at 0, increasing to 1, and then 2. It's important to note that although lists begin at 1, our grid positions always start at 0. This is called being 0 indexed, in case you're interested. Talking about indexes, our next variable of interest is the index variable. This represents the item number in our actual list for the grid cell under our mouse. Here, let me fill the first grid cell. See how item 1 of the list now shows a hash symbol. This represents an impassable wall. Moving across to the next cell, you can see index is reporting 2. So it is no surprise that if I fill this cell, that item 2 now gets a hash 2. I'll do the same for 3 and 4 to complete the row. So pausing there, can you guess which item in the list will get a hash if I was to fill in this tile next? Yep, it's item 5, the very next item. And what about the top right cell? Which item in the list represents that? Yep, it's the last item in the grid list, item 12. So, the final unmentioned variable is tile, and this simply reports the item in the list for the grid cell the mouse is hovering over. Hashes for filled tiles, and nothing for empty ones. Splendid! Let's get scratching! We'll begin then by coding up a simple tile grid like the one you saw. Start by removing Scratchcat, sorry mate, and add a new sprite, naming it Grid. Switch to bitmap mode and zoom right into the drawing canvas to draw an 8x8 square. In bitmap mode, it snaps easier to exact sizes. Try to start exactly one checkered square above and to the left of the costume centre, and end one checkered square below and to the right. Great job. You can check the size here. Make sure it is indeed 8x8. OK, now to the Code tab. When green flag clicked, make a variable tile width for all sprites, and set it to 120, just like in our example. Next, make grid columns for all sprites. Right, we can calculate the number of 120 pixel columns that will fit on the screen. Start by dividing the stage width, that's 480, by the tile width variable, which will be 120 right now. But we just need to ensure that we round the results to a whole number. I'll use a floor block around the divide to round it down. Next, we make a variable named grid rows for all sprites. Duplicate the above script and change it to set grid rows, and use a value of 360. That's the height of Scratch's stage. OK, 2 more variables to add. I didn't tell you about these. Offset X and offset Y, both for all sprites. This may not be a scrolling project, but nonetheless, we need to offset the entire grid to ensure that it is drawn touching the bottom left corner of the stage. That's an offset X of minus 240 and an offset Y of minus 180. Time to make our first custom block. It's never too early. Name it Scan. And for the time being, leave the Run Without Screen Refresh box unticked. I know, right? What's going on? So, drop a scan block at the end of the green flag script. For the purpose of this tutorial, we need to enable the pen extension. So click the Extensions button and select the pen extension. Bring in and erase all to clear anything that might have been drawn previously. Our first mission is to correctly size the tile sprite. Remember, we drew its costume to be 8 pixels wide, and yet we set the variable tile width to 120. Use a set size block and begin with a size of 100%. The costume right now, therefore, would be 8 pixels wide, as designed. But if we divide that size by 8, well, 8 divided by 8 is 1. That's 1 pixel wide for sure. The beauty of this is that now that it's 1, we can multiply the width by tile width, and then the sprite is certain to become tile width pixels wide. Just what we wanted. Excellent. Except for our project, I'd prefer a 1 pixel gap between tiles so that we can see the edges. So I'm just going to subtract 1 from the tile width before we're multiplying it. Now, set Y to offset Y to move it to the bottom of the stage. We'll create an outer loop that draws each row of the grid one at a time using a repeat grid rows. So, how to draw a grid row? Start by setting X to offset X to bring the sprite to the left edge of the screen. Now repeat again, this time for grid columns. We begin by stamping our very first tile, and then prepare to stamp the next one by moving to the right using a change X by tile width. That is a whole tile to the right. This inner loop then repeats until the first row is stamped. Before we loop back to stamp the next row, we need to move our sprite upwards. Use a change Y by tile width. Remember, our tiles are as tall as they are wide. Great, then the outer loop is safe to continue and begin stamping the next row. This continues until the entire grid is complete. We can give that a test. Click the green flag. So this is close to being correct. The only flaw is that we begin positioning our tiles on the bottom left edge of the screen. But our tiles are centered on the midpoint of their costumes, so end up with half their tiles off screen. We need to move the entire grid half a tile to the right and up. We can do this by adding tile width divided by 2 to the offset X and offset Y. Running the project again, and the problem has gone. Great! I get a lot of satisfaction out of perfectly aligned graphics. Guess that's why I love my grids. Why don't we try tweaking the tile size down from 120 to 40 pixels instead? Running that. Yeah, so nice. You can see more clearly the order in which the tiles are drawing too, left to right, and then gradually filling bottom to top. This is in contrast to the tile scrolling tutorial, if you are following that series, where the tiles filled from bottom to top, and then gradually left to right. Now there's no real right or wrong order to do this in, but it just so happens my preference is actually the way we are doing it in this project. Our next trick is to implement the image scanner. But before we can do that, of course, we could really do with a costume to scan. So make a new sprite, naming it Level, and draw an interesting level costume. I'm personally drawing the most amazing, awesome mega spiral ever created. There. Genius. Now click back into the grid sprite. And we'll add in an if-else before we do the stamping, checking whether we are touching sprite level. You could use touching colour here if you preferred, but just be aware that touching colour is considerably slower. So always use touch sprite if there's no other good reason. So, if you are touching the level sprite, then we'll set ghost effect to 0. That is, the tile is fully visible. Else, set ghost effect to 80. That will make it very faint, but we'll still be able to make out the edges of the tile, which is really a nice way, allowing us to see the grid for now. Give the project a run. Ooh, notice wherever the grid cell contains any part of the level sprite, the tile gets filled in with a solid stamp. Everywhere else, dim. Problem is, this grid resolution is just a little bit too low to make this very exciting. So let's try reducing the tile width to 20. Aha, now we are talking. We can actually make out the spiral pattern much better, but perhaps at the cost of speed. Not a problem though. Right-click to edit the scan custom block and switch on the wonderful run without screen refresh. Yay! Here we go again. Oh wow, yeah, that's better. That scan took no time at all. Let's try a tile width of 10 then. Cripes! Scratch is eating this for breakfast. Perhaps we might venture a size of 6. You ready? Whew! That's better than we might have hoped. So quick. And look at the detail we are getting in our level scan. There's no comparison to the tiles we were using for our pathfinding tutorial. You can see why this method is so tempting. But, have you noticed? Did we forget something? Where's our grid list I promised you? Well, alrighty then, let's do this. Make a new list, naming it Grid, and tick for all sprites. Since we are scanning a whole new level in the scan scripts, start them then by deleting all from grid. Now in the inner loop, each time we stamp, we want to add a tile value into our grid list. However, we'll actually do the job in the if condition. This way we can add a hash when we touch the level sprite and add an empty value when not touching the level. Either way, we add just one value per grid cell. Well, that's it actually. Wasn't so hard, was it? Run the project. Right, well something happened. Look, the grid list now contains 4,800 items. Let's take a peek in the list. There are certainly runs of hashes in there, and lots of empty rows too, as expected. It's quite hard to inspect with such a lot of tiles. Let's ramp back a bit and set tile width to 60. There, that's easier. We now only have 48 tiles in the list now. If I scroll to the top, you can see that the first 3 items are all blank values. This correlates perfectly with the bottom 3 cells of the grid in my example. Scrolling on through the list, I can see that there are then 4 hashes in a row, and this again correlates to the 4 filled in tiles. I'm happy that this is working as intended, so let's move on. Having this data in our list is a triumph, but in itself is pretty useless, until, that is, we can read the values back out in a meaningful way. For example, given a position on the stage, tell me the value in the list for the respective grid position. Is it a hash or a blank? Now that would be very useful. I think we can manage that. Make a new custom block named getTileAtX with an input of x and a label of y, followed by an input of y. Tick to run without screen refresh. To use this block, we'll bring in a new when green flag clicked. Repeating forever. In here, place the getTileAtXy, and we'll look for the position of mouse x and mouse y. This block needs to give us back all the details of what's at the location on the screen. Firstly, we need to work out the grid x and y that the mouse is within. Start by making the new variables grid x for this sprite only, and grid y, also for this sprite only. Just set grid x to the input x and run the project. Let's look at what the values reported by grid x are. Minus 240 on the left and 240 on the right. The grid x needs to start at 0. No negative values here. We can get this by subtracting offset x from x. Run it again and confirm that the left edge now reports 0. Cool. Now each tile is tile width pixels wide. Therefore, we divide this new position by tile width to give us the count of tiles we have across the level. Test that again. Yeah, so on first inspection, this looks a little off. But look closely. You can see that the number on the left of the decimal place is the correct grid x value. It's just that we have a fraction part to the number 2. We can remove this by rounding the value down to the nearest whole number using the floor operator. Oh yeah, perfect. That's the correct grid x. Let's do the same for grid y. Set grid y to the floor of y, subtract offset y, divided by tile width. We can test that works too. No problem there. Grid x and y are both showing the correct 0-indexed grid position of the mouse cursor. So make a new variable, naming it index for this sprite only. Here we go. Set it to grid x plus 1. This is a good start. If I test that, you can see that the bottom left tile is reported as index 1. After all, lists always start at item 1. Moving to the right also increases as expected. Now we just need to account for the up and down too. Now remember, we know how many cells are in a grid row. Moving up in the grid by 1 row is the same as moving right by an entire row of cells. That number is stored in grid columns. So change index by grid y multiplied by grid columns. Testing that reveals a very hopeful result. The cell above the first cell reporting 9 as expected, and the top right cell reporting 48. That matches our list length and therefore the number of cells in the grid. I think we've got it. To make certain, let's find out what is actually at the position in the grid list. For this, make a new variable named tile and set it to item index of grid. Now click the green flag again. So what are we seeing? Look at the new tile variable reporter. As our mouse moves over solid tiles, we are seeing a hash, and then over empty tiles, we see the empty value. This is most certainly working as planned, and we are able to read these values out of the grid list based on the X and Y position on the screen. Okay, so, just for kicks, set tile width to 20. Yeah, that's too cool. You may be thinking that all this seems like a lot of work to do what we could already do with a touching sprite. But this is just the beginning, and we'll find this method has the potential to do so much more, and also run way faster than using the touching sprite block. Believe me. So, the last part of our tutorial is focused on being able to set the position tiles based on a tile index alone. In our example here, say we want to place a tile at index 6. So what is the grid X and grid Y of that tile? Okay, well, first things first. In our code, add in an if block under the getTileAt block and check whether the space key is pressed. Now the index variable is already set from using the getTileAt block above. We can therefore replace item index of grid with a new hash character. I can run that, and if I hover over the bottom left tile with an index of 1, press the spacebar, and hash character is added to the list successfully. Look, I can skip one and add one in for 3 and 4 too, but nothing is drawing on the screen. That's right, this list is not linked to the screen in any way. No, it's a scan of what the level first looked like. If we want the level to change to reflect this new change, we'll need to do it. So, make a new custom block naming it position@index with an input of idx. That will be the grid index we want to position and stamp our tile at. Run without screen refresh. We'll begin by converting this index into a grid X and Y. So, working this out is all based around division. Look at this example. We want to find the grid X and Y of item 6, yeah? So start by remembering that list indexes begin at item 1. So we have to adjust for this by subtracting 1 from the number 6. Right, we're left with the number 5. Now we use division, and we're dividing 5 by the number of columns in this grid. That is 3 in this example. So how many 3s are there in 5? Well, 1. Remainder 2. Now look, see here. Isn't this at grid X of 2 and grid Y of 1? Coincidence? I think not. It's quite plain to see that the count of full rows will give us how far up the index cell is, and the remainder is how far across we are. Awesome! Do we have a maths operator in Scratch that gives us the remainder after division though? Well, yes we do, and it's called modulo, or mod for short. So set grid X to idx minus 1 and mod this against grid columns. Grid Y can be set by dividing idx minus 1 by grid columns and then rounding down to the nearest number using the floor operator. Right. Lastly, we just need to set X to offset X. Mustn't forget that. Plus the new grid X multiplied by tile width to space them out correctly. We'll do the same with the set Y to grid Y multiplied by tile width, all added to offset Y. Just got to plug that in now, So after we were replacing the item in the grid with a hash, we can insert a position at index of the index variable. This will position us correctly on the screen for the grid cell of index. So set goes to 0, and then we stamp. Are we there? Exciting! Run the project. I'm going to stamp the bottom left cell. Press the space key. Underwhelming. We have succumbed to the half tile issue once more. Back into the position at index script. We need to move half of the tile width to the right and up. And look, we are already multiplying by tile width, so it's easiest just to add half to the grid X and let the multiply take care of the rest. The same goes for the grid Y. Just add half. And this is it. Run this project again. Yeah, these tiles are very much more aligned. But well, it bugs me. But the last tile I draw never looks as lined up as it should. I've got it. We are seeing the actual sprite here, not the stamp. They are slightly out from each other. No big deal. We can hide this issue. Literally. At the bottom of the scan script, stick in a hide block. But we must also then add a show block to the top of this script. Otherwise, the hidden block will not work when we ask it whether it is touching the level. That will break our scanning altogether. Can you tell I've fallen into that myself a few times? Splendid. Run the project, and I'm feeling that we are 100% OCD compliant. Oh yes, much better. You can see that the newly placed tiles are also showing in my tile value as I revisit them. So, although we started by creating a scanning project, you can see that we might very well use this project without the need for this at all. Like if I hide the level sprite, we can start with a blank slate and draw our level ourselves. Well, there's loads of ways we could branch out from here, but this is the end of the episode for today. I'm aware that this project has not ended with a really complete end product, but I'm happy enough with that because there are so many exciting things ahead. All I would say though is if you want to play with this project further, and I'll encourage you to do so, make sure that you create a copy of it first from the file menu. That way, you have a backup to return to, ready for the next part when it arrives. In the meantime though, let your imaginations run wild and see what you can create with this. Don't forget you have the option to switch to detecting colours with the tile scanner if you have an idea for that. Or think of how you might use the getTile@XY blocks in cool, novel ways. Right guys, if you've enjoyed this video, please hit the like button. And if you're not subscribed to this channel yet, then what? Why not? Do it right now. You really don't want to be late for my next exciting episode. Finally, if you'd like to support this channel, you now have the option to join my membership. If you're a kid, then of course get your parent to help out. After all, it's worth it. We do the best Scratch tutorials and some fantastic learning here that you won't get anywhere else. It's the best way to help me make this channel the best it can be. Oh, and did I mention you get perks? Win-win! But until next time, Scratch on guys.